Welcome to the Overview of Spark lecture. Before we begin the setup and coding of Python and Spark, let's discuss what Spark is in the context of big data. We'll begin with a general explanation of what big data is and then the related technologies. So again, the general things we're going to be covering in this lecture is the answers to the question, what is big data? Give an explanation of Hadoop, MapReduce, and Spark, talk about local versus distributed systems, an overview of the Hadoop ecosystem, and get an overview of Spark. Now in this course, when we're actually coding, we'll be working with the Spark Python API, which comes in the form of a library called PySpark. But in order to really understand why you would need to use that and what the purpose of Spark is and what problem it's trying to solve, you need to understand Hadoop and MapReduce and the entire big data ecosystem, which is why we're going to talk about that here. So first off, what is big data? Well, let's say you have some data that can fit on a local computer, somewhere in the scale of 0 to 32 gigabytes, maybe even 64 gigabytes depending on how much RAM you have. That kind of scale of data is not big data. Even if you have somewhere between like 30 and 60 gigabytes, it's still large enough that conceivably you could buy enough RAM to just fit it all in your random access memory. That's memory that is used when you open up something like an Excel file. Everything's just stored onto RAM and you have quick access to it. But what do you do if you end up having a larger set of data than what you can hold onto RAM? Well, now you have a couple of options. You can try using a SQL database to move storage onto a hard drive instead of RAM. Or you can use a distributed system, something that distributes the data to multiple machines and computers. And this is where Spark is going to come into play. If you're using Spark, you're at a point where it no longer makes sense to fit all your data on RAM, and it no longer makes sense to fit all your data into a single machine. So what is a local system versus a distributed system? Well, a local system is probably what you're used to. It's just a single machine, a single computer. It all shares the same RAM, the same hard drive. A distributed system looks something like what we see on the right. You have one main computer, some sort of master node, and you also have data and calculations distributed onto the other computers. And what you can do in a local system versus a distributed system is your local system, you'll be limited to however many cores are on your local system. That is, however much processing power or however much storage you have locally. But in a distributed system, what you can do is leverage the power of a bunch of weaker machines to eventually have more cores or more capabilities than even a strong local single machine. So we can see here on that local machine we have 4 cores, but what we can do with distributed machines is get a bunch of weaker servers or weaker machines with less power, but distribute either the data and the calculations across all those machines to take advantage of a distributed system, which is kind of at the crux of what Spark is trying to do. So a local process will use the computation resources of a single machine, while a distributed process has access to the computational resources across a number of machines connected through some sort of a network. And after a certain point, it's much easier to scale out to many lower CPU machines in a distributed system than try to scale up to a single machine with a high CPU. And distributed machines also have the advantage of easily scaling. All you have to do is just add more machines. Versus a single computer, no matter how nice it is, there's going to be a limit on how much RAM or how much storage you can add to a single machine. So with distributed machines, you can just keep adding systems to the network and just get more power that way. And they also include fault tolerance, which is really important when you're talking about large data sets. If one machine fails, the whole network can still go on, which you can't do on a local machine. If your local machine crashes due to some error in the calculation, that's it, you just lost all your calculation, all your data. And fault tolerance is a fundamental idea where you're going to be replicating your data across multiple machines, so even if one goes down, your calculations and your data still persists and goes on. Now let's discuss the typical format of a distributed architecture that uses something like Hadoop. So Hadoop is a way to distribute very large files across multiple machines. The issue of taking one large file and storing it onto one machine isn't really that complicated of a task. It's quite trivial. But the idea of grabbing a really, really large file that no longer sits on one machine and distributing it in a way that makes sense across multiple machines was quite a complicated issue back in the day, and that's what led to the creation of Hadoop, which uses the Hadoop Distributed File System, or HDFS. And you may have seen that term HDFS when you've read stuff on big data. And HDFS allows a user to work with really large data sets across a distributed system. What's also super important about HDFS, it duplicates blocks of data for fault tolerance, which is the idea if one machine goes down in your system, your data is duplicated on some other machine, so it still continues. It also uses what's known as MapReduce, and MapReduce allows computations on that distributed data. So we kind of have two fundamental ideas here. Hadoop's distributed file system, which is the way that we get a really large data set distributed across multiple machines, and then we have the idea of MapReduce, which allows computations across the distributed data set. So for distributed storage, you have something that looks like this. Again, you have some sort of master node or a name node, has its own CPU, its own RAM, and that basically controls the process of either distributing the storage or the calculations to these other, sometimes known as slave nodes, these other data nodes with their own CPU and own RAM. So what HDFS does is it uses blocks of data with a size of 128 megabytes by default, and each of these blocks is replicated 3 times. And the blocks are distributed in a way to support fault tolerance. So a machine can go down, but your data will go on. So smaller blocks provide more parallelization during processing, and multiple copies of a block prevent loss of data due to the failure of a node. And MapReduce is a way of splitting a computational task to a distributed set of files, such as Hadoop Distributed File System. And it consists of a job tracker and multiple task trackers. And this idea of trackers is also going to go on with Spark. So in the context of MapReduce, the job tracker sends code to run on the task trackers. And then the task trackers allocate the CPU and memory for the tasks and monitor the tasks on these worker nodes. So what we covered can be thought of in 2 distinct parts: using HDFS to distribute large data sets, and then using MapReduce to distribute a computational task to a distributed data set. And next what we're going to do is learn about the latest technology in this space, that second half of it, known as Spark. And Spark improves on the concepts of using distribution. So we're going to continue talking in this lecture, just an abstract overview of Spark, Spark versus MapReduce, what Spark RDDs are, and then Spark data frames. Spark is one of the latest technologies being used to quickly and easily handle big data. It is an open source project on Apache, so you have access to all the source code, and it was first released in February 2013 and has exploded in popularity due to its ease of use and its speed. And it was created at the AMP lab at UC Berkeley. And you can think of Spark as a flexible alternative to MapReduce. So don't think of it in the concepts of Hadoop versus Spark, but instead of MapReduce versus Spark. And Spark can use data stored in a variety of formats, including things that are stored on Cassandra, AWS S3 storage, Hadoop Distributed File System, and more. Now let's take a little bit of time to discuss the idea of Spark versus MapReduce. This does dive in a little bit into semantics because sometimes people phrase things in a way that's a little bit confusing, but I want you to get the idea that it's Spark versus MapReduce, not Spark versus Hadoop. So a lot of times you'll hear the discussion of Hadoop MapReduce versus Spark, and then people kind of shorten that to Hadoop versus Spark, but that's not really a good analogy or comparison. But let me explain why sometimes people say Hadoop MapReduce and then just shorten it to Hadoop. The reason is MapReduce, remember, that's the half that actually distributes the calculation. It requires files to be stored in a Hadoop distributed file system. So because of that, people tend to put Hadoop and MapReduce together as kind of a single phrase. And then when they discuss Spark, they'll say Hadoop versus Spark. But really it's MapReduce that you're comparing with Spark. Spark can use Hadoop distributed file system, which is why it doesn't really make sense to say Spark versus Hadoop by itself, because Spark can actually work with the Hadoop distributed file system. But Spark can also work with a wide variety of data formats, which is why we kind of always hook up Hadoop with MapReduce. But Spark can work with not just Hadoop distributed file system, but quite a wide variety of file formats. But more importantly, Spark can also perform operations up to 100 times faster than MapReduce. And that's one of the big selling points of Spark, and that's what you hear a lot of times when you're reading about Spark online. So the question is, how does it actually achieve this speed? 100 times faster is a huge increase in performance. Well, MapReduce writes most data to disk after each map and reduce operation. Spark will keep most of that data in memory, that is something like RAM, after each transformation. And Spark can spill over to disk if the memory is filled. So if you don't have enough RAM on that single local machine, it can spill over to the hard drive. But the main idea here is that as computers and RAM have gotten cheaper, it makes sense to just put everything onto RAM instead of writing and reading to the hard drive. And that's one of the main differences between Spark and MapReduce as kind of a high-level overview. Now let's talk about just Spark in particular. At the core of Spark is the idea of an RDD, or a Resilient Distributed Dataset. And Resilient Distributed Dataset, or RDD, has four main features: a distributed collection of data, fault tolerance, parallel operation, the ability to be partitioned, and the ability to use many data sources, not just be limited to something like Hadoop distributed file system. So what does this actually look like? Well, usually you have something that looks actually really similar to the MapReduce framework that we talked about earlier. You have some sort of driver program and a Spark context, or even a Spark session when we talk about Spark 2.0, and you have some sort of cluster manager and then your working nodes, that distributed system. Now, what does this actually look like physically? Well, you have something that looks like this: a bunch of servers somewhere, maybe AWS is your provider of them. You just link to them online, and you have this master node and sending back tasks, and the slaves send back results. And on those worker nodes, or sometimes called slave nodes, they have the data cached to RAM/disk. So RDDs are immutable, lazily evaluated, and cacheable. And there's basically two types of Spark operations. There's transformations and actions. Transformations are basically a recipe to follow, and then actions actually perform what the recipe says to do and then return something back. And this behavior of transformations versus actions also carries over to the syntax when coding. A lot of times when you write a method call off of a data frame, which we're going to be working with PySpark, you won't see anything as a result until you call an action, something like show. And this makes sense because if you're working with a really large data set, you don't want to constantly be calculating all the transformations. Maybe a transformation can be something like take the average, or take the count of a particular data, or show me where column X is greater than the number 2, etc. like that. But you don't want to actually calculate that every time until you're sure you want to perform it, because it's such a huge data set, it's quite a task to calculate everything every time you type something. So that's why everything is separated between transformations and then those calls to action. And we'll see this more when we actually begin coding with PySpark and Spark data frames. Now there's one last point of confusion that arises that I want to clear up right now. When discussing the Spark syntax, that is what you're actually going to be coding, the syntax of the code you type into a keyboard, you will often see RDD syntax versus data frame syntax show up. Now with the release of Spark 2.0, Spark is moving towards what's known as a data frame based syntax. So if you worked with something like Pandas or R, or maybe even like an Excel spreadsheet, those are more like data frame. You have columns and rows. But keep in mind that the way the files are being distributed physically can still be thought of as an RDD, the Resilient Distributed Dataset. Your data is still being stored in a resilient distributed manner. So RDDs is still the way it's happening physically, just the syntax of what you're working with is now called data frames. So it's just the type syntax that is changing. Alright, so we covered a lot, but I don't want you to worry if you didn't memorize all these details, or if a lot of this went over your head and left you maybe a little confused. We're going to cover a lot of this again and again as we learn more about how to actually code with Python, how to code with Spark, and utilize all these ideas. This should just give you kind of a very high level understanding of what a distributed system looks like, why we actually phrase things as Spark versus MapReduce, and maybe how Spark works with RDDs, at least at a very high level. But again, don't worry if you didn't memorize all this. We're going to cover this a lot more as we continue coding throughout the course. Okay, so a quick note on Spark data frames, which is what we're going to really focus here in the course. Spark data frames are now the standard way of using Spark's machine learning capabilities. And Spark data frame documentation is still pretty new and can be a little sparse. I think it's actually getting better, so we'll take a brief tour of the documentation just to show you what you can expect and how we're going to cover this course and kind of blend in the documentation so you have the skills to reference the documentation, because it could be a little mysterious at first. So I'm going to jump over to spark.apache.org in my browser, and you can just Google Spark or Apache and it'll probably take you there. And we're going to explore the documentation together for just a little bit. Alright, here I am at spark.apache.org, and you can already see here they tell you that it can run programs up to 100 times faster, and note here it says Hadoop MapReduce, not just Hadoop. And it runs even 10 times faster on disk. That's when it goes to the hard drive. And it's also ease of use, so we can write applications in not just Java or Scala, but we can also do it in Python and R. And as I mentioned, we're going to be working with Python in this course. And then it also has generality, so it can combine SQL, streaming, complex analytics, etc. But let's kind of scroll up here and talk about what we're going to be working with. This course is going to work with Spark 2.1. And if you click here on the latest release documentation, it'll take you to the link of Spark Overview. And this is where it kind of describes downloading, running examples in the shell, launching on a cluster, where to go from here, quick start, etc. And as we explore Spark more and more, we're eventually going to run into what's known as data frames, datasets, and SQL. This is going to be one of the first things we cover, and this is essentially the way you can work with Spark with datasets. So basic data analysis, cleaning up your data, munging data. We're going to be working with Spark SQL and Spark data frames. And essentially Spark SQL is this platform where we build on top of to get datasets and data frames. And the reason it's called Spark SQL is because it has the ability to execute SQL queries. So if you already know SQL, you're going to be able to use that SQL knowledge to filter out your data based off a SQL query. And we'll cover that later on in this course. And as you continue on through the documentation, you'll notice there's these nice little tabs that show you the Scala, Java, Python, and equivalent R code. Now, not every operation is available in every language. Now, something that we haven't really discussed yet is that Spark itself is not a programming language. It's just a framework for dealing with large data and distributing it and doing those calculations across a distributed network. Spark itself is written in a programming language known as Scala. So the Scala API for Spark is the one that gets the latest features, which makes sense because Spark is literally written in Scala. It's going to get the latest features. Now, Scala is actually written in Java. So Java, a lot of times, also gets a lot of the latest features. The APIs for Python and R are usually a little bit behind on the latest stuff. So keep that in mind. A lot of the more advanced things or the latest technologies with Spark, sometimes it takes maybe one generation or one more release cycle to get to Python, and then maybe an extra release cycle to get to R. But creating data frames, all this stuff, you can kind of see here how it looks like a table. We're going to be covering this in an entire section talking about data frames. The last programming guide I want to show you is this MLlib guide. And if you click on that, you basically see the machine learning library guide. And this is something we're going to be referencing a lot throughout the course, especially in that second half on machine learning. But you will also notice that it has this RDD-based API guide. And this is kind of what I was referencing when I talked about RDD syntax versus data frame syntax. And there's this big announcement with Spark 2.0, we're already on 2.1. The data frame-based API is the primary API, which is why we're going to be focusing exclusively on the data frame-based API. And honestly, it's a lot easier to work with. It makes a lot more sense than the RDD-based API, so it's a welcome change. And you can see here, you can click on the main guide or just check out particular topics. Maybe you're interested in clustering. So you click on clustering, you're interested in k-means, click here. It gives you some information about k-means and shows you examples for Scala, Java, Python, and R. So that's definitely stuff we're all going to be talking about and focusing in a lot more in the second half of the course when we talk about machine learning. But I do want you to know that the documentation is all here for you. It's pretty good for MLlib. Maybe you're interested in collaborative filtering, so you come over here, scroll down, and they show you a full example. But they also have the API documentation. So if you click here on Python, this will take you to the API docs. So come over here to Spark SQL functions. That's something we're going to be using a lot. And then it tells you basically the pure API, as close as it can to the actual source code without clicking here where it says source. So if you click on that, then it will actually take you to the source code itself for further explanation. Now, usually we'll just be referencing the documentation, not the actual API docs. This is more heavy duty, especially if you're hitting the source code button. But this is about as far as we're going to get. If you ever have questions or want to dive deeper into what certain functions do, you can check out the API docs. All right, so I know that was a lot, but hopefully that kind of clears up some misunderstandings of Spark and why we're going to be using it, what's its purpose, etc. I will see you in the next lecture where we'll probably discuss how to actually install, set up, and get everything running on your computer. I'll see you there.